Okay, this is a split stator for a wind turbine. It's split in only as you make it as two halves, a left half and a right half. The advantage is you can take take it out of there one side at a time without disturbing the magnets or the shaft or the blades or anything else. You just take the bolts out of the outside out here. The red line is the parting line on the casting for your epoxy, and I put a piece of polyethylene milk carton, bent around on the ends, in the mold. It's guaranteed there's insulation there between these two coils, since there's going to be a voltage difference between them. You have your A, B, and C wires for the for a phase going around here, and here's where the end of the phase comes out. So green hooks to green, hooks to green, hooks to green, right on around. Same thing with those. And what you end up with is 3 wires down here at the bottom, going from one side to the other. Only 3 wires. I don't care how much stuff you got up there. There's only 3 wires goes across that. You're cutting the phases in 2, and then a heavy wire or a bus bar would go across that gap. There's an advantage to this arrangement. If you want to stutter your 2 coils at both ends, take one of these pieces, since the bolts are symmetrical, flip it upside down, and you got a stuttered coil arrangement. Let's show you that here real quick, and why you would want to do it. Probably more important. These are rectangular blocks. They represent the stator coils. CW means it's wound clockwise. CW means it's wound counterclockwise. Up at the 0 position, well, actually it's coming up onto the 360 degree position. You have 2 counterclockwise together, and 180 opposite that, you have 2 clockwise together. And there's a reason behind this madness. It's still a 3-phase generator. At least at this point, it's a 3-phase generator. We're going to change that in a minute too. This is just because circles are easier to draw than squares. You can use a compass on a circle. You can make this out of poster board, and you can make it out of plywood, whatever you want. Plywood and an Irwin speedboard bit. But the thing is, you got the a top piece with all your coils colored or marked somehow, somewhere that's easy to tell. Colors are nice, and they have a hole through it in the center of each coil, right wherever the coils are. Below that, you have another piece of poster board or another piece of plywood with a pin in the middle, so you can turn one compared to the other. I've actually got, because I'm doing it in the computer, I got a handle on the next layer down, so I can spin it around and watch the north and south magnets, what they're doing to these coils as it turns. I got one for, in this case, one for blue and one for red. Purple's turned off. It's not connected for this phase. It's going to change to blue and purple with red turned off, and then red and purple with blue turned off. There's 2 more pictures beside this for all 3. Oh golly, I did it again. View, set view, top. Same picture. Okay, just for different colors, and a third one. Okay. And this is a visual aid. If you take your actual number of coils and magnets, and see the magnets, there's a different number of magnets than there are coils. Otherwise, when they all the magnets came across a point, generating electric and go, plus to minus, it's going to have like a stopping point. And you'll have one at every location. that's a whole lot of magnetism that you're trying to jar off of where it is. But if you have a different number, then it doesn't cog. The more you got, the less it cogs. But anyway, I have a mask sheet I put over this when I'm playing with it that only leaves the red showing, because I'm going to look at it one phase at a time. The least confusion you can have while you're trying to sort it out, the better. So I drop a piece on here, and I can turn it around to it leaves the reds in the open, and it covers up the greens and the blues. And at that point, what I have is the coil, a hole, and you can see a magnet starting to come through there. It's got a red X, it's a red magnet. And they're marked north and south. So I can see that if I just arbitrarily say that counterclockwise means a north polarity on the coil, that you can make it either one, but one's got to be the north, and that will make clockwise a south facing. So if this was a south magnet approaching a north coil, then they're going to attract. If this was on the other side leaving, and it was the opposite polarity, you'd be pushing it away. I do the analysis on this as a generator, and I sort of think of it like a three-phase motor. It's sort of in the background, because it's a three-phase device. But as soon as you take and you start moving things around, or you have sometimes you're going to have all the coils wound the same direction. And the way you determine this red arrow means that this red coil is trying to turn this axle that direction. So think of it like a motor for this part of it. Think it like you're doing a motor rather than a generator. So when this is approaching, if this is a north magnet, this would be making a south polarity coil. It's going to try to turn that wheel this direction. And when you're doing the blue one, you should get exactly the same direction on there. They always seem to work in pairs, no matter how many coils and magnets you got. And you'll notice that all the way around this ring, all the arrows are trying to move it in the same direction, okay? If you don't have the stutter step here, you're going to find that half of this set and half of this set are trying to turn in the opposite direction. If you've wired all your coils in series, then one is feeding backwards to the other one, and in other words, these two that are going the wrong way cancel out two that are going the right way. And of course, I got a lot of coils. There's 30 coils and 32 magnets. So I'm taking 4 of my 30 out of the picture. And if 3 of like if this zone was also affected, then I would be taking 6. I'd be taking 20% out of the power output for no reason, because you can fix it. Now, some combination numbers of coils and magnets, there's not much you can do with it. This trick doesn't work. But it works on this particular example, and that's what I'm building, because I need a pretty big wheel. The first thing I'm doing is a motor. This is the coils for the motor. Actually, everything to scale. Everything in the drawing that's apart is to scale. 1 inch goes 1 inch. You can print it, and it's an inch. But I'm doing a motor for a 21-foot diameter fan. So I've got a 2-foot diameter stator. Well, the coil part, the stator itself is bigger. You know, it's just plastic though, and some connection points out. It's empty plastic. The working parts are, they're 24 inches on the outside. And the generator, we're going to use the same exact parts on the vertical axis wind turbine, except that I'm going to flip half of my stator to get 2 together and 2 together. And when you do that and you run the analysis, all the arrows go the same way. Before you flip it, you're going to have a couple of them that go the wrong way. Now this makes perfectly good sense. I've got 2 more magnets than I've got coils. And it makes sense that they're all working for you for 180 degrees. It's hard for it to be anything else because it can only jump ahead by one magnet position. Because there's only two difference. In half a turn, there's only one difference. One more magnet than there are coils on a half a rotation. So it makes sense that all these things are going to pretty much fall in line no matter how many you have of one and the other. But as soon as you cross that line, it starts working against you until it's completely out of phase back up at the top. So that's what I come up with, was just putting, just stuttering ahead and starting off with clockwise on the second half instead of, this should have been a counterclockwise. I just shifted them all around, and the one that I took off up here, I put down there, which is basically what you do when you flip that side over, upside down. Anyway, this is a visual aid, and the arrows, I had a video here, I'm going to post it. I didn't put it up, I'm going to post it. Probably just before this one, because this is part of the explanation for it. Maybe I'll put this one up for the other one. I didn't mention that these arrows had some meaning. I think I mentioned that the ones pointing out are disconnected. They're not trying to turn it in either direction. But I don't think I hit on the fact that the arrows pointing in a direction is the direction that the shaft is trying to turn. Either it's being turned by the wind turbine blade, or it's being turned by putting electric to the stator coils. But there's a relationship between the magnet and the coil that rotates the shaft. Otherwise, you waste your time building the thing. Is that all I got to say? That might be all there is to this. Anyway, this is a visual aid. I invented it in its current state. I've never seen it anywhere else. However, the original idea came from a YouTube video, and I don't have the man's name. I didn't record where I got it. I'd sure credit him if I could. Obviously, nothing up here is copyright infringement if it's original work. Or maybe it is, I don't know. But if it is, you're free to use it. You're free to copy it. You're free to share it. Whatever all those little tabs are, you can do what you want with anything I put up. He had just two wheels, and you had north and south magnets, and they had different numbers of them per rotation. So he had one piece of paper, just typing paper, he put holes in it so you could see the ones down below, and then he labeled the ones at the top. And as he turned this thing, it showed the interaction of all those magnets. Now, what he was trying to prove was the free energy motor, dynamo, whatever. It's the size of a couple of 12-volt batteries out of your pickup truck. It's a device you can set on your table. It's put in some like 3/4 inch plexiglass or glass, all glued up with silicone. And in the bottom, you got a like an electric window motor with a rubber tire on it, and a starter solenoid off of a GM car that can rotate it up to where it touches this rotor of this thing. Okay, that doesn't make a lot of sense, but if you listen to it a couple of times, it'll start to make sense. Anyway, the wires come out and they're all sealed to the case. They pull a vacuum on the case, get rid of as much air as they can. As long as the case doesn't implode, you're good to go on the vacuum. Anyway, they have a wire that makes the starter solenoid and jacks the windshield wiper motor up to touch the side of this rotor. It's got like a flywheel that it runs on. So you hit the switch, the windshield wiper motor spins up, and 10 seconds later the rotor's at full speed, and you drop the motor away and it's just shut off. So what they're trying to do is prove that this makes free energy. So you have an output, a plus and a minus output out of the thing, also sealed up coming through the glass. And they put a multimeter on it set to milliamps, thousandths of an amp. And it reads like 13 or 12 or 13 milliamps. That's where the thing falls apart. Because you've got no load on your two wires, you can't read the amps that are going through a load. There is no amps going one side to the other. There's no load. What you're reading is the inductance of your multimeter. this, uh, anyway, a number goes up on it, and they show you that the next day the number has fallen very little. Did I mention this thing is sitting in zirconium oxide, what they call ceramic bearings, ceramic races, ceramic balls, you know. They run with no oil, no grease, run forever. I'm getting some for my ceiling fans in the house here because I'm tired of having to rewind fans. Anyway, with no real air in there, and what air there is free to spin around with the rotor, you're just waiting for the bearings to have their negligible friction slow down a 10 kilo chunk of metal. It's, you know, probably turning 1,500 or 2,000 RPM. So he hasn't, in my opinion, he's not proved that the molar free energy device works. It's an awful lot of iron to get no output, and if you put that through a light bulb, I'm sure it would stop in about 10 minutes. Because all you're using up is the kinetic energy in the rotating parts. The reason it can turn, and nobody seemed to point this out, is hysteresis and inrush current. When you have a coil, nothing going through it, and you connect electric, the immediate reaction is 3 times the amps that it takes steady state. They call that inrush. That's what burns up big industrial motors as they get stalled for some reason. If the starter can't knock it off, it's pulling 3 times the amps. The windings are 4, and it just smokes the windings. All the smoke gets out, and you're off to your English sports car place to get replacement cans of Lucas smoke, which you put back in the wiring under your hood. I diverged again. Let's see here. Oh, inrush current. Because the inrush is a lot higher than steady state, that sort of works for you. And the other thing you get is, if probably in high school they gave you a little piece of wire and you wrapped it around a screwdriver and hooked it to a 6-volt dry cell battery, made an electromagnet out of the screwdriver, and you pick up some nails or tacks or whatever on the table to show you that you've made an electromagnet. Then you disconnect the wire, and 2, 3, 4 seconds later the first nail falls off, and then pretty much all of them fall off. It's because you made residual magnetism. You make that metal is still magnetized, even there's no current through the wire to magnetize it. It's the metal has lined up the lines of flux, and it stays magnetized. It's decaying all the time, and it's an exponential decay. But there is a brief bit of time where it stays magnetized, not under power. So if you switch your power positive to negative, you get this huge inrush, and you also have residual magnetism, which you can have lapse or overlap cycle time to what it takes to go from one phase of the cycle to the next. I think you can probably, I wouldn't guarantee it because I've not built one of those things. I can't waste my time on stuff I know is not useful. But you could probably get something which would run for months on that little bit of principle. Some kind of driving a MOSFET or probably something with a gate built in. You want the lowest possible energy consumption and heat dissipation you can get, because all that's going to slow it down. You're losing the energy you're working with. Anyway, this guy turning these 2 pieces of paper, one with holes and one with just circles around the outside. You could watch the stuff go across the holes and see what's going on between the magnetic flux and the coil or a second magnet, whatever you got. And it was one of those slap your forehead things that says, now wait a minute, I've been trying to figure out and watching what other people are doing and what gauge wire they used and how many turns was that fella, and we wonder where they got all these numbers, and all of a sudden you can look at it and see what it's doing. And then I added the part about putting the external arrow out here to decide whether it was trying to work for me and if it acted as a motor working for me, would it tend to turn the shaft in which direction? And I found out somewhere one way and somewhere the other way. Predominantly one way, but some going the wrong way. That's counterproductive. So I found out if I made the coils alternate clockwise and counterclockwise, I cured a lot of it. Got it down to like 2 segments screwed up. And then I noticed that they were all within like 1 magnet of actually working for me. So I just rotated the stator around, just moved the coils around by 1 coil location, and everything went working the same direction. So that's what this tool here is and what it tells you. If one phase, you don't have to do it for one phase. I did it for all 3 because I was experimenting, trying to find things out. But if one phase works, there's equal number of coils and magnets for the second phase and the third phase. It'll do exactly the same thing. It's not like they all turn and go the opposite direction on the next phase and cancel everything out. They all go the same direction because the coils are not changing polarity. And that's pretty much all we need to talk about here. This is sort of a supplement to the other video, so I need to put both of them up. That video was about, in case you're not going to watch it, I'll tell you. For different AWG sizes of magnet wire, you can download this if you just do an image search on images.yahoo.com or Google for specifications on magnet wire. It'll have 40 lines with the 40 different sizes. This is a few of the lines, 14, 16, 18, 20, and 22. There's also a 15, a 17, you know, it's continuous. This is the ohms per 1,000 feet of wire. Doesn't make any difference if it's single, double, triple, or heavy insulated. It's the copper is what you're looking at. This is the amps that wire can carry. This is the diameter of the wire. That makes a difference. After you've got it down to 1 of 2, you have to make a choice which you're going to use. Yeah, I drew a little diagram. Shopping list is things to buy before I come back. I'm in the Philippines. Well, what the little diagram was a square that was the width and height, the space I have to put coil windings. And I have them laid up, make a line and another line of the little diameters of circles, and count how many you can put inside of that cross-sectional area. The more wraps, the better. If you can get more wraps than you come up with down here in your calculation, oh golly. If you come up with more wraps than the calculated value, this one has to have 58 wraps. It's for 48 volt brushless DC motor, and the calculations are not hard. Once you stick them in the calculator, you just keep adding a divider or a multiplier or something, and you don't have to take any numbers out. If it's the 27 decimal points, that's what you can get. Okay. 2.3 amps, that's the amps that a number 18 wire will carry 2.3 amps. If I use 6 of them in parallel, that comes out to 6 times 2.3 is 13.8. Divide by volts by amps, and you get ohms. V equals IR, right from high school. And you divide that and find out what fraction of 1,000 feet that is. And because it's 1,000 feet, they were thinking, right? That tells you how many feet of wire you need. The coils, like in my case, I got 10 per phase. There's 2 phases on at a time. One feed's positive, and then it goes through the other ones as a negative. So I get 10 coils plus 10 coils out of the 30. There's 20 in use. So I divide my feet by 20, get the number of feet of wire I need, times 12 inches of the foot. Total inches of wire per phase, and this number here I've changed because I was just trying to figure out which gauge of wire I had here, and I just drew a sort of a, looks good to me, coil and measured the average wrap diameter. And that's what I come up with for that sort of fake coil. But the real number is 7.731. So this wraps will go down, I don't know, maybe to 38 or 40. But there's 6 of them. The 6 of them are connected together at both ends, so it's basically like a single wire. And the ohms up here are for a single wire, right? If you have 6 wires, they're all getting 1/6 of the current here, and they'll generate 1/6 of this because it's 1/6 of that. Then you add the 6 back together, you come up with the same thing. That's just in case you don't want to watch any other video. But there's a bunch of other stuff in there. As an incentive, this is 2 half-width coils done on the same winder at the same time. The center 6 wires and the other one will be right beside you. You connect them together so your ins and outs are both on the outer end of the coil, and they don't have to go underneath of the coil, taking up width on your space you have available for windings. You know, if you have to take out a wire diameter or more just to get the wire out to where you can connect it to something. See, the magnets are sweeping across both faces. You can't come up through the center. It's got to come underneath of it and stay inside of the stator casting. Okay. There's a bunch of stuff on this sheet, mostly related to the whole house fan. This is just the electrical end of the thing. Okay, we're going to stop now. If you learned anything, you can give me a thumbs up. I've got 5 on my 70 videos so far, and I've made it to a view count of 5 on one of them. Still some of them with 0, but I'm hopeful they'll take off in another year. Anyway, if you don't like it, you can give me a thumbs down, and you can make the first comment so that I can find out why you didn't like it. If you want to see other videos, which are titled more to what the focus of the channel is, which is building a giant concrete house in the Philippines, all the techniques we've come up with and what it looks like, and rebar and cement ratios and all that kind of stuff. It's house building. And there's when I got bored, I put a section up on stitching glue and other kind, and metal hulled boats, how to design them, how to make full-size patterns and print them, stuff like that. But there's not many of that. It's mostly house building. And then there's the vertical axis wind turbine one. I highly recommend the tricks in that one. It's a boosted turbine. If you have a horizontal axis, the only energy you can extract from the wind is what touches the blades. And if it doesn't touch the blades, if it's free area, it's not like the disc area in a helicopter. It's because the speed is not as high as a helicopter. All that air that goes straight through without disturbing the blades, you're not getting anything from it. A vertical axis wind turbine is even worse because you have blades that are receding, going the direction the wind is traveling, and you have blades that are advancing, which are working against you. They're trying to turn the shaft the wrong direction. So I come up with a way to get around that, and if the turbine is 8 feet tall, 5 feet across, the blades, it's a cylinder, standing on end. It could be horizontal, but it's standing on end. The thing is that I'm capturing the wind on 3 times the cross-sectional area of that cylinder, and it all goes through the blades, and when it exits the other side of the cylinder, it pushes it again in the same direction, and all the air coming on the receding part of the thing is blocked. It's a booster arrangement. I guess it's unique, but it's not this totally from outer space. California Wind and Energy, the utility company from the state of California, They have boosted turbines, but they're only using one part of the air, but they're using a booster to get a lot more energy out of it, and it works really well. And I saw a video and I said, well, I wish I could boost this thing. Well, I guess I can. Let me look here. And I started scribbling, and an hour or two later, there we go. Anyway, that's in a video, free to look at. You have to click the icon at the left of the video because typing in the channel name doesn't work for some reason, only for my channel. It works for everyone I watch, but doesn't work for mine. And you found this because I didn't put the normal kind of title on it. I put a title of what this is. So I expect I actually probably get 4 or 5 views on this one. I might get as much view time on it as it took to upload it, which would be nice. Okay, y'all have a fine day, and I hope you learned something. All right, I'll turn this off. Will not go off. Just will not turn off. I'm gonna have to save that whole blasted